There's also another interesting variant of SQL injection. This method we refer to is known as Automated SQL Injection. Several years back, manipulating SQL queries was not considered prone to automatization. And the fact that even blind attacks were managed by trial and error seemed to support this claim. An attacker needed to see some returned information and react to it in the correct way. The procedure would tend to look dissimilar most of the time. This belief proved false, however, when a new type of attack cropped up in 2008. Judging from the scale of infection, it was extremely dangerous. It was less vicious, however, as far as its results were concerned. The aim of the attack was not to break into systems, but to sniff out credentials to social networking services or online gaming sites. At any rate, over 1 million websites were hit in the attack. What sites were ripe for this attack? The sites that were hit were above all written in ASP, Microsoft technology. The second factor was that the sites were connected to a Microsoft SQL server. Thirdly, the targeted application would dynamically create SQL commands and forward them to URI addresses. If you looked at the entire address in a browser, you would see there a parameter equals parameter value call. To attack a site like this, it was enough to send it something similar to the string you can see in the slide. This method was practically fail-safe. If some of you haven't yet decoded the above message, we'll try to break it into a more readable format. We need to find a service that is vulnerable to SQL injection and constructs queries in the way that you can see below. We need to check the responses from a web application to the supplied queries, or to the applications to a web server. As you have probably all noted, all of the URI addresses contain encoded SQL commands. If we were able to decode them, you would see that they look like this. These are simple SQL commands. Take a look at the server reactions. If the reactions match your expectations, you have found a perfect target for an automated attack. You can send them the following SQL command. This is the long encoded fragment you saw before. We know that we can place SQL commands inside URI addresses. This means that we can insert the above command and execute it at the end. As we mentioned, over 1 million websites were vulnerable to this attack. Why was the number so large? Since an efficient attack technique has been developed, why shouldn't it be automated? A program for this popped up rather quickly. As you can see, the program's interface is not displaying correctly. To be able to see what's written there, you need Chinese fonts installed in your system. The application works by submitting one of the previously seen tests into a web search engine of your choice. Click Search, or what we think is search. The pane below will list websites that are prone to and ready for an SQL injection. Let's now see what the SQL code looks like. But before this, a few words of introduction. There's two aspects. First, we'll try to see how the information on the database and database structure can be obtained so that we could execute some commands later. We'll also move back to a topic that was broached earlier, two quotes. There are two apostrophes in all commands we saw earlier, just like this. Why is this constructed in this manner? All presentations here are demonstrated inside the SQL editor window and not in a client application. Because of this, we had to simulate in some way a code excerpt that was executed by a client application itself. To make it look as close as possible to the real code sent by a client application, we split it into 3 rows. The first and third row are constructed by an application, except the double dashes in the third row. The dashes should be at the end of the second row, but if they were in this case, the command would not work for us. Since the double dashes are an end-of-line marker, what's beyond them is irrelevant. They make an attack far less complicated. It doesn't matter if they're followed by 2 or 3 apostrophes or no apostrophes at all. We don't know what is ahead in the command, and we don't need to know that. All we want is to make sure that it won't be executed. Let's see what will happen after executing this query. This function is exclusive to Microsoft SQL servers. Remember that we're again dealing with ASP.NET, which is sure to be connected to a Microsoft SQL server. After the query is executed, the server introduces itself. We now know the version of the server. We'll quicken the pace a little. It's obviously possible to read a table row by row in a way that was shown earlier. You could look up error messages to see the contents of individual rows, but this presentation would take ages in that case. Let's speed things up a bit. Imagine that row displaying has been factored into the outline techniques. We'll simply read more than one row at a time. We know that this version of SQL Server is sure to contain a table named systables. Knowing the version, we know this for sure. We also know the structure of sys.tables. It's well known and publicly documented. So let's try to ask the table for some data. We still can't enter any arbitrary values, but we can add code to part of the command formulated by the application. This means that we can, for example, add something like this. Column names in the result are obviously incorrect, but we can see that there are some tables contained in schemas and that they have identifiers as well. If we were really determined, we'd read this row by row until we found a name that draws attention. Apart from knowing the table name, also the names of columns are required. Let's send a similar query, this time referring to sys.columns. This made us discover the names of columns and the names of tables in which the columns are contained. The next part is quite easy. Let's come back now to one of the queries. We could, for example, focus on employees. The identifier of the table can be inserted in another query. Once it's executed, it's visible that there really is a table there that has some specified columns. You can check birth date, gender, and other employee data. We'll anticipate things a little. Assume that you're interested in identifier, title, gender, and login. This is more than we can take. By a general rule, we can only request 3 values at a time, since the table that is used by the original query has only 3 columns. This can't be changed. You can instead ask for 2 or 3 values in a single column. The results include identifier, title, login, and gender all clumped together. You can't do it in any other way. An hour or 2 pass. After analyzing the database, we've realized that additional employee information is contained not only in the employee table. It can be found also in the contact table. The tables are joined in the employee ID and contact ID fields. We've discovered this in an iterative process. Now we simply wish to read the data. Since we can't do it in any other way, this will be done in 3 columns again. As it turns out, we have the first and last name, a passwords hash, and the data we've seen before. This information is pretty interesting and we can work around it. To be honest, we don't need to search any further. At the end, we should only erase a table that contains a log of our activities if it exists. This turns out successful. There's no prompted error message. We'll at last take a look at an automated attack. After decoding the string you've seen in one of the earlier slides, the following code excerpt will appear. Two variables and a cursor are declared. Then the cursor reads names from system tables. This will be performed exactly like before. The difference is that other system tables are used here. Next, the code will check whether user table data is read, and check if a column is a text data type. If it is, looping through the rows in all found tables, all found text data type columns, the code will execute an update command. A script is inserted to a current table, to a selected text data type column. We can execute the code because instead of exec, we're using print so that the data in the database is not modified. All the columns to which the script are injected now contain the following code. What this means for a web application and its users is that everything that's displayed in their browsers is now an active element. By clicking anywhere on the page, visitors connect to the site above and execute the code that is added to it. This script is constructed to steal credentials from visitors. This is the end of blind SQL injection attack used in conjunction with cross-site scripting, an attack type that will be discussed in a moment.